Hello guys, welcome back to my YouTube video. The name is Richard and it has never changed. So this video has taken me a little bit while to shoot because I was looking online and trying to find resources to better understand the state and state functions of and then also process functions of thermodynamics. But looking online, all I see is complex graphs and nobody actually making the links on like a very low level so that everybody could understand it. They treat it as entities standing alone. I try to bring everything together so that we know what the process functions and the state functions are. So the last part of this thermodynamics or thermochemistry is the states functions and then the process functions. To begin with, we started with systems, and then we said these systems could be in three parts. Could be isolated, it could be closed, or it could be open. And these systems could also change state. We change from solid to liquid to gas. And the changing the state is called they are undergoing a process. And then we said that those process would require you change any of those state functions. So today we are going to go through the state functions and then the process functions and how they link together. So there are according to the MCAT or at the standard of the MCAT, there are just two process functions. So the two process functions are one, heat, and then two, work. Right? How does heat and work relate to each other? Let's say we have a system. Let's say we have some type of a hydrocarbon. Let's say we have, just something that is a system. This system, as it's being there by just existence, the mere existence of this system has internal energy. So we have first we have a system, right? So let's say a system, right? And then this system has internal energy. Now, where does this internal energy comes from? Like I said, if it is a hydrocarbon, the internal energy is literally the bonds that are existing between the atoms to make up the compound, right? If it is just, let's say, any type of molecule is just a bond, or any type of compound is just a bond. Those are the internal energy. And the internal energy, right, is given by the heat that is being added into the system. So internal energy is represented by a U, right? And this U is given by the heat that is being added into the system. The heat over here is represented by Q. So we could say Q over here. The heat being given by the system minus the work done by the system. The work done by the system. So once you know this equation that the internal energy is the heat that we could add into the system. So any heat that the system is going to use to form the bonds and everything as such. And the work done by the system, could be if it's a gas, like a hydrocarbon, is it expanding? Is it burning? Is it changing state? If the system is doing any work, it is taking energy from the system. That is why the internal energy, U, is equals to Q minus W. But this Q over here, which is the heat over here, has an expression of its own. This Q is equals to, so let me, bring it down here. That this Q is equals to the mass, right, times the specific heat capacity times change in temperature. Now this is where it gets a little bit tricky. The Q, which is the heat in the system, is equals to the mass of the system times the specific heat capacity of the system times the change in temperature. That is the very distinction between heat and temperature. See, for us to be able to quantify heat, for us to be able to do anything at all, to do a measure heat, there should be a temperature difference. That is why there is a change in temperature over here. Now, let me draw your attention back to this thing, the system, right? Let's say we have the system of the hydrocarbon system that I told you about, or the system of anything at all, and we bring this system into thermal equilibrium, or into thermal contact, not thermically, into thermal contact with another system. Now, when we say thermal contact, what do we mean? There are three ways that a system can be in thermal contact with each other, and those are: one, convection, right? Convection is when the system is immersed in some type of fluid, water, for instance, right? If it's in a thermal contact and the boundary between them is a fluid, that is convection. Or it could be in conduction. Conduction is if the system is in equilibrium, is in a thermal contact, and what is between them is a solid material. That is conduction. It conducts the heat through this solid material. And two, and the last one is radiation. So radiation over here is if there is nothing at all. There is no air, because the air acts as a fluid. Air is a fluid. So it will be convection. Radiation is vacuum. There is no air at all. So in space, the sun and then the earth, they are in a radiation contact. So the thermal contact between the sun, which is a system of itself, and then the earth, which is another system of itself, is radiation, because there is nothing in between. Not even air molecules is there. There is nothing at all. So that is radiation. Now, if a system is brought into thermal contact with another system, heat would flow, or there will be a change in energy, just so that, like anything at all, anything, any matter on the planet, any system at all, if you bring them to close enough together, they want to be in equilibrium. They want to be the same. That is why seesaw rotates. That is why matter form. That is why energy even transmits between each other, because all systems wants to be the same. They wants to balance the scale. So if we bring a system which is under a thermal contact into another system, it wants to what be the same with that system. So if this system has heat in it, the heat is going to flow to the other system because of the change in the temperature, right? And now temperature over here, this is the different one another way to establish the difference between heat and temperature. Temperature relates to the absolute thermodynamic um, um, kinetic energy, right, of the system. So the temperature is related to the kinetic energy, how the particles are moving. The average kinetic energy of the particles moving is temperature. The change in this temperature, if the particles were moving super fast and now they are moving super slow, the change in this temperature is what we call heat, right? So the thermal energy or the heat would flow from one system to the other system. We got that done. So back to what we were saying, a system has internal energy. The internal energy of that system is given by the heat in that system minus the work done in the system. We got that already. And we said if a system is brought into thermal contact with, then a thermal contact could be convection, conduction, or radiation with another system. The systems, the both of them would want to be in equilibrium. So energy or heat would flow from the system that has the highest heat. And the way we know this has the highest heat is if it has a higher temperature to a system that has a lower heat, which will have a lower temperature, right? That transfer is called the heat. And the reason why, and this makes the reason why heat becomes a process um function, because it's a process function, because it is in the process of transferring, going. That is why heat would become that. It's in the process of transferring or going. That is why heat is a process. It's a process function. And then work two is a process function because it is in the process of doing something. It's working, it's doing something. These things, that is why I said these things is not just poof out of thin air. Somebody has to sit down and think about these things to bring them into, so it has to have connections with whatever the person was thinking about. That being said or that being done, we are moving forward. Now, the heat that is transferring, if it is transferring under a constant pressure, now we told you that pressure was part of the state function. So let me just list all the state functions over here. It goes when I'm feeling pressured and dense, all I want to do is to watch TV and get hugs all day. So the enthalpy is DH. Entropy, internal energy, and then the Gibbs free energy. So, and as I said earlier, the system already has internal energy. So internal energy has already been covered under our state function. The system already has internal energy, and this internal energy is given by the heat the system has. So heat has already been also covered, and minus the work done. So the work done over here has also been covered, right? So heat, internal energy, heat done, and heat, and then work has been covered. Now, if this system, which the heat is moving, right? If the heat move under constant pressure, let me do it so that my board will not be used all up, all the way over here. If the heat move, wait. No, I have it. Okay. If the heat move under constant pressure, the heat move under constant pressure, the measure of that heat energy, under constant pressure is what we call enthalpy. Get it? When the heat moves under constant pressure, the energy is what we call enthalpy. So, and when the heat moves, so enthalpy over here is also covered. Enthalpy is represented by H. It's also covered over here. And let's say you have a system, right? Like you have that hydrocarbon I told you about, which has an internal heat already. The internal heat is concentrated. Now you brought the hydrocarbon near to another system, and now the heat is moving from this hydrocarbon to the system that you bring it close to. The heat, which was now very concentrated in the hydrocarbon, is spreading out to go to that other system over here. Now the spreading of this heat is called entropy. Where is it? It's represented by S. The spreading of the heat. Now you could say the spreading of the heat is the entropy, but it is the measure or the change in how the heat spreads, right? So in other words, you could also say it's just the spreading of the heat is the entropy. So the heat spreading, the spreading of the heat is what we call entropy. So entropy over here is covered. And once again, the enthalpy that I said over here, it is the measure of heat under constant pressure. The pressure over here is also covered. So you see how these things, all of them link together, how we are linking all of these things together. And then also over here, I told you that a system, right, for us to measure the change, right, even under constant pressure, for us to measure the change, there should be a temperature difference. So the temperature has been also covered. And we said the temperature is equivalent or it relates to the average kinetic energy of this hydrocarbon that we already had. Now, see volume over here. You'd say, how does volume occur, or how does volume even gets over here to, or density? How do these two come over here to be part of these state functions? Now, for us to measure heat, which is in enthalpy, for us to be able to measure it, there are two ways that we could measure heat accurately. Now, one way for us to measure heat accurately is by using a tool called calorimeter. A calorimeter is a tool that measures the calories, and calories is energy, right? And this energy, the transfer of this energy is the heat. So we can use a calorimeter to measure heat. There are two types of calorimeters. One, we have constant pressure calorimeter. Constant pressure calorimeter is basically everything that we use in our everyday lab to do the lab experiments. And then also a styrofoam cup, the coffee cup that you usually have your coffee in from Starbucks. It is a perfect example of constant pressure calorimeter. Why is it a perfect example? Because you have your coffee cup over here, right, which is covered with a lid. Now your coffee cup is covered with the lid. The pressure incidented on this lid is the atmospheric pressure. No matter where you move on Earth, the atmospheric pressure is 1 atmosphere. Doesn't change. It's constant. That is why it is constant pressure calorimeter. Now, this is basically, everything that we use, how experiments are being performed in our day-to-day activities, they are all constant pressure. And another way that we could measure heat is constant volume calorimeter. How do we use constant volume calorimeter? This is where it's also get a little bit tricky. What you have to do is now you have to get your hydrocarbon. You have to build a system. So you have your hydrocarbon, right? You put this hydrocarbon in a chamber, a steel chamber, and you add oxygen into this steel chamber. So we have our oxygen gas here. And then you connect this steel chamber to an ignition source. Could be a battery over here. So you have your ignition source over here. Ignition source over here. Now you have your ignition source. This whole thing, you dip it in water. So you have this, and then you dip it in water. So over here is just water, right? So you have a system that you have closed it, and the system is in contact with this other, is in another system, which is water over here. And you spark the ignition. So once you spark the ignition, this hydrocarbon will burn in the presence of this water molecule. Now the volume over here is not going to change because you've limited the volume to how much ever volume of this steel there is. So once it is burning, it is only the hydrocarbon over here burning. The oxygen is just being used as fuel. So whatever energy, and mind you, the water here, we know the mass of that water already. We have to know the mass of the water we dipped it in. Whatever energy that is being burned here, it is going to be absorbed by the water, right? So the energy of this system, which is the internal energy of that system, is going to be the same as the internal energy is going to be the energy absorbed by the water, right? But then since the system is losing the energy and then the water is gaining the energy, the system is losing minus U, and then the water is gaining the energy. But so this is how a constant volume calorimeter is done. And then you could go ahead over here, right? And then say that since this is the system, and then a system is going to be so Q into bracket minus Q of the system over here, minus the W of system, because U is given by Q minus W, is equal to over here U the Q of water minus the W of water. But what you should know is that since our volume was constant, the volume didn't expand. Since the volume did not expand, the work done is zero, because work done, right, is equals to the pressure change in volume when we are dealing with this calorimeter. But then there is the change in volume is equals to zero. So it makes the work done zero over here. So since the work done is zero, this can go to zero. This can go to zero. So now we could get the Q minus the Q of the system is equals to minus Q is equals to Q of the water. And then we say the Q over here is equals to what? The MCAT. So the Q would be the M into bracket minus M of the system. Let me now use S for system. The specific heat of the system times the change in temperature of the system is equals to over here the Q, the M of the water, the specific heat of the water. And specific heat of the water is always given to you as what? 1 kilogram per whatever. It will be given to you because it's a constant. Times the change in the temperature of the water. And as I told you, when we was dipping the mass in the water, the mass of the water is always known. So when you meet a question like this on the MCAT, this is always known. The C over here is also always constant. And then the change in temperature would be given to you. So then you could solve for your questions just by understanding how the system even works. See how I never even memorized any equation. By just understanding how the systems work when they are in contact with each other, I'm able to derive the equation that I need for myself without putting any huge quantum equations in my head. Just understand the systems and it will work perfect for you. So let me clean over here. Yes. All right. So after all that, I have cleaned this. How that density comes into play over here? Now, density comes into play over here because of density's association with volume. Density is equal to the mass over the volume. So if we say that the volume over here is a state function, automatically density would be part, because density is just an expression of the volume by how much mass of the substance you have. So that is how density also plays a role over here. So now we've linked how all of these things work together, except Gibbs free energy, which is down here. Gibbs free energy. Now, how does Gibbs free energy also comes in here? This is also another fun stuff. Gibbs free energy comes in here because this dude over here dictates whether the heat will transfer in the first place, because Gibbs free energy encompasses all of this for the system which is have the internal energy, for that internal energy for the Q of the heat to flow at the constant pressure or the spreading out, or is dictated by the Gibbs free energy. The Gibbs free energy over here. Now the Gibbs free energy is G. G is equals to enthalpy, which is H, minus a temperature change in entropy. You see how enthalpy and entropy, enthalpy is the measure under a constant pressure, and then the entropy is how the system is spreading out. Temperature over here is determining how the heat is even going to transfer. See, the change, how the heat is even going to transfer, that's the temperature represented over here. This would dictate whether the system would even transfer its heat spontaneously or not. Like, if it doesn't meet the requirements for the Gibbs free energy, it's like the security check. Bro, if you don't meet my requirements, you're not even going to go through any of this. So just forget about it. It's the first requirement you need to meet. So if the system would undergo all this process spontaneously, the Gibbs free energy has to be less than zero. So the Gibbs free energy has to be less than zero for the system to undergo a spontaneous reaction. Now, how would see if we see the in what conditions should the system be in for the Gibbs free energy to be less than zero? Right. If the system is minus over here and we want it to be more than zero, then this function over here, the temperature change in entropy, has to be bigger. See, there are some of these things, if you understand these things and put it at the back of your head, it will be very easy when you meet a discrete questions on the MCAT that will state that, oh, there is a system, blah, 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 blah. Under what condition should the system undergo this reaction spontaneous? And then it gives the answer solution. At a high temperature, a low entropy, at a medium. See, those are all of it. And then you just know that, see, if my temperature is big and my entropy is big, chances of my system going under spontaneous reaction is really high. If my temperature is low, my entropy is low, and my entropy is low, but my enthalpy is high, chances of it going under spontaneous reaction is low. So if G is bigger than zero, it's non-spontaneous. Right. And that is how all of these functions relates to each other. Now, once that is done, I've related this to each other. There are a couple of things that I need to also bring attention to so we could close our chapter on this and we could move to the next topic. So you pause it. Okay, so the next thing we're going to talk about is heat curves. Heat curves. Now, the heat curves, I will draw like a big Y Cartesian plane, like the one we used when we was dealing phase changes, right? Now, heat curves is simple. It's basically similar to what is it called? The states or the state change of the system. We have a pressure against volume over here, right? And then our heat, we start from like zero, right? And let's say over here we start from a solid substance. Let's say we started from a solid substance, right? Yes, let's say we started from a solid substance. If we want to change the state of the sample, right, from solid to liquid, we have to keep on adding heat, which is energy, right? So let me over here. I think here will be energy, right? You have to add energy into the system, or let's say heat into the system for you to be able to melt it. Let's say you have a solid ice. For you to melt it, you need to apply heat. So as you keep on applying heat, you keep on applying heat until you reaches the melting point of this ice. And the melting point of this ice is 0 degrees Celsius, right? So let's say you've reached 0 degrees Celsius. Once you've reached 0 degrees Celsius, any amount of heat that you apply anymore, it's not going to raise the temperature. The temperature is never going to be raised. So over here, it's going to plateau. Why is it plateauing? It is at a phase change. That is why we're doing heat curve. So at a phase change, any temperature that you add into the system is going to use that temperature or the heat to convert whatever mass of the system that you have into the next phase before the temperature would increase. So once you get here, the temperature plateau, right? And then once everything has been converted into water, it can now rise again. So over here is the melting point. So once it rises again, so here is solid melting point, then it goes into liquid, right? Once it gets here, when it gets to the boiling point of liquid, so here is the boiling point. when it gets to the boiling point of the liquid, it also plateaus. And every heat that you add to it, or every energy that you add to it, is going to use to convert everything into a gaseous water. So over here is going to be gas. Until everything is converted into gas, the temperature do not change. So that is basically heat curve. Now I drew like a very, straight lines, whatever, but in reality, it is a curve, right? It goes like this, goes like this. It's like a good curve, like the S curve, right? But to understand it and to be able to quantify it, we draw a straight line like that. Now, as we said earlier, if we are moving, the state changes from solid to liquid is melting, back is freezing or condensation. You do know all of those stuff. But the tricky part here is that over here brings us to, or introduce us to, what we call the Hess law. The Hess law tells us that it does not matter the path that you take, it doesn't matter the process, function that you take. The summation of an energy that you use to convert a system from one state to the another, or the total energy that you use to convert a system from one state to another, is the sum of the energy at different stages. So if we ask you how much energy did we use to convert from solid to gas, it is basically from solid to the melting point, from melting point to liquid, from liquid to the boiling point, from boiling point to gas, and from gas to whatever. So you can name here A, B, C, D, E. So from the Hess's law, from A going to B, from B going to C, from C going to D, and then from D going to E. If you are supposed to sum them, the energy that you use at each stage is going to be the total energy that you use. It does not matter whether you came here, you decided to go back down, whether you came, you decided to dip up, branch left, go tangential, it doesn't matter. It's just the sum of all the energies that you did use. A tricky part under this way that the MCAT would test you is that at the phase change, over here, when you are asked to calculate the energy, now during over here when we are adding the heat, you could always use the Q is equals to, another way to remember this formula is Q equals to MCAT, which is the exam you are going to write, and the M is the mass specific heat temperature change. But once you get to this phase change, you cannot use Q is equals to MCAT anymore, because the change in temperature over here is equals to 0. So anytime you use Q is equals to MCAT, you're going to end up 0. But we did add energy to it. But then it's giving us 0. So how are we going to find the energy? That's why we go Q over here is equals to the ML, where L over here is the latent heat. So if it's over here, is the latent heat of melting. Over here is the latent heat of vaporization. So the L is equals to the latent heat. So if you were over here is the latent heat of melting. If we are at a liquid trying to go to gas, it is the latent heat of vaporization. Do not forget this formula. Q equals ML. And don't forget Q equals MCAT. So if you remember these two formulas, you can solve the phase change questions. Just that the calculation will be lengthy. I'm sorry. I don't know if there is a shortcut to go around it, but you literally has to do the calculation at every step. And then after that, you sum all the heats that you got from all those points, and that would be your total heat according to the Hess law. To the last part and get rid of this chapter, let's talk about standard heats. Heat. You see, you've been hearing the word heat. One of the most abused word in chemistry. Now, when we talk about standard heat of formation, it is basically the heat needed to form 1 mole of a compound from its constituent elements. That is basically heat. So it goes like this. Basically, it's an enthalpy, right? So that an enthalpy of a reaction, which is the standard heat of formation, the enthalpy of a reaction is going to be the enthalpy of the formation of the product minus enthalpy of the formation of reactants, right? So basically, that is the standard heat of formation. It's like that. And then from there, we have another one that we call the standard heat of a reaction, which is going to be the sum, the sigma sum of the standard heat of the products minus the standard heat of the reactants. It's basically similar as when we started coming from equilibrium. It's always product first and the reactant second. And then from there, we can go to the bond dissociation energy. So a bond dissociation energy is also an enthalpy, right? Bond dissociation energy. It's basically the amount of energy you need or you require to break a bond, to break the 1 mole of bonds to break bonds in 1 mole of a compound. It's basically the bond dissociation energy. And you could calculate that by using going off of this same, because for us to form products, the bond in the reactants needs to be broken. So whatever this enthalpy changes is the energy we use to break those bonds. So it's just going to be the contextual understanding is what will get you through a lot of these things. And after that, we can talk about another type of heat. I think the standard heat of combustion. Simple. It's just the heat attained from burning a fuel. Simple. These things are just the standard is just in front of them to throw you off. You can go off of by this one equation over here, and you could fix it to meet your specific demand. One thing that I want to draw also attention to, and then I promise that will be the end of it, is these terms. Endergonic, right? Endothermic, and then is it endergonic, and then endogonic, right? Endogonic, and then exothermic. These things would really confuse some people, so much so. But see the endergonic and then the endogonic, these two things over here has to do with actual energy. This is what the Gibbs free energy represents. So the Gibbs free energy that we said, it is the enthalpy minus temperature change in entropy. If you say J is less than 0, which means the system has to take in energy. This is negative. It is endogonic. And if it's the opposite, it is endergonic. But this exothermic and then endothermic is temperature. After the reaction, the temperature, right? So do not also confuse these two things, right? If after the reaction, the temperature is less than what we begin with, or the system took up, or let's say after the reaction, the system spews out heat into the environment. So we do the experiment. Let's say you have some type of metal, you dip it in an acid, you bring your hands close to it, it is a little bit hot. That is exothermic, spewing out heat. If the system has to take heat, if you literally have to put fire onto the system to burn it so that the experiment would occur, it's taking in the heat, it's increasing its temperature. That will be endothermic. So that is the key differences between these, and it really gets people on the MCAT a lot. So just understand that one you see the tendency endo, exo, and when it's X in it, just know that when you have the X in it, it has to do with the temperature. And when you have the gonic in it, it has to do with energy, right? And that will be the end of the chapter 7 of the MCAT chemistry review. The next one would be, let me see, what is it? Is it redox reaction? It's going to be gas phase, one of my favorites too. Thank you very much for watching this video. See you in the next one. Peace out.